Bismillah, alhamdulillah, wassalatu wassalamu ala rasulillah, wa ala alihi wa sahbihi ajma'een. A'udhu billahi minash shaitan rajim, bismillah ar-Rahman ar-Rahim. Ma'bad. Thank you very much for attending today's lecture. Today's lecture is on the understanding of solar depression angles and their role in determining the start of Isha and Fajr Salah in England. Now, as you know, in the last few years, there's been a heated debate regarding the times for Fajr and Isha. Most mosques have their own timetable. Some mosques do it an hour earlier, pray Fajr an hour earlier, some mosques an hour later, and there's general confusion amongst the masses as to why this is happening. This talk is a humble attempt to use astronomical data and bring to light why this happens, and it's for you, the general public, to make your own minds up as to what timetables you would like to follow. Okay, so from the beginning I'm going to start by defining the prayer times, and I know most of you know the times for Salah, but I need to do this to build up the issues regarding the different opinions regarding Salah times. So, Fajr Salah, it starts from true dawn, as-subh sadiq, starts when the sun is 18 degrees below the horizon, and it's identified by a white light that spreads across the horizon. So if you're observing Fajr, you'd see the sky, you'd see the whiteness kind of appear and spread across the horizon. That's the time for Fajr. So it's important for establishing your suhoor. You need to make sure that you're praying, you've stopped eating at the right time, because if you don't, as you know, then you've eaten into the prohibited time to eat and you have no fast. Beware of false dawn, the zodiacal light. I'm going to get into this as we go on as to what this is. Now this is dawn. This is what dawn looks like. If you're observing the time for Fajr, you'd see the white light that would appear and then spread across the sky. And obviously as dawn carries on, as the sun gets closer to the horizon, you'd see a red light as well. Most of the sky at this point is still dark, especially the other side of you. It's still going to be black because the first crack of dawn appears on the other side, towards the east. That's a very early picture of, that's very early dawn. You know, it's just just happening. So you can see the whiteness of the sky. The rest of the sky is still black. You can still see the stars. That's the planet Venus on the ecliptic, and that's Orion. It's facing upside down. So there are two dawns. So we have a true dawn and we have a false dawn. Now many people they see Fajr. I've actually seen this before as well, where if you are observing the time for Fajr, or if you're an astronomer, at various points during the year, it's towards the spring and winter equinoxes, especially in England. Most parts of the world you can possibly see this every night if your skies are dark enough. You'll see what looks like the sun appear, but it's not the sun appear. It's an illusion. It's actually what's known as subh kazib. It's a false dawn. And now we're going to talk about that as we go on. So Fajr is not what appears in the sky like this and also someone like that. It's what appears like this. So if you see a light appear like that, that's not. Be reassured, it's not Fajr. It's a phenomena, and it will disappear, and you'll have darkness again, and then Fajr will start soon. So Dhuhr begins once the sun has crossed the celestial meridian, true north, exactly halfway between sunrise and sunset. So you got sunrise and sunset, the point midway in the middle. Once the sun is at its highest point and it's just crossed it, that's the time for Dhuhr to start. Now, that may not necessarily be at the highest point in the sky. Depending on where you are, that would only be at the highest point. It'd be directly overhead at the equator. Apart from that, nowhere else on Earth would it be directly overhead. So you can deduce that by looking at the shadows. When you don't have a shadow at the equator, or when you have the smallest shadow you can detect during the day, just after that point, sundials will show you this. That's the time for your Dhuhr. So Asr, late afternoon, how to detect Asr started if you don't have a clock. The sun is cooler, yellower, and it's lower in the sky. There's a difference of opinion on when this starts. The Imam Malik, Imam Ahmad bin Hanbal, Imam Shafi'i say this is when the object of a shadow is 1 times its length. Now Imam Abu Hanifa says the shadow needs to be twice its length. So you've got a stick in the ground, and the shadow of the stick is this much at noon. So what you do is you add on another shadow length of the object. That will give you the time for Dhuhr. According to Imam Abu Hanifa, 2 shadow lengths. take into account the original shadow. It's important that you take into account the original shadow length at dawn. So Maghrib starts when the solar disk is completely below the horizon. It's important due to prayer and breaking fast, because you need to know when Maghrib is. Most timetables for Maghrib, by the way, give you elevation levels of at sea level. Now most cities are higher than sea level, so we need to factor in that and add a few minutes. So we'll talk about that as well. Comes back to optical actual sunset sightings. Most time, I should talk about that as we go on. So lasts until astronomical twilight. So Maghrib time will last until the time for Isha, which is when astronomical twilight totally disappears and you have complete darkness. Now that varies season to season, latitude to latitude. Isha time, again there's a difference of opinion, starts when the whiteness of the sky disappears. This is the opinion of Imam Abu Hanifa. So the whiteness is the last light to disappear when it's 18 degrees below the horizon. When the redness of the sky disappears, this is the opinion of the Sahibain, Abu Yusuf and Muhammad Ibn al-Hasan. The solar disk, 18 degrees below the horizon again. Yeah, it's the difference of opinion. Safer to follow the 18 degrees, especially for northern climes like England, Canada, America, Russia. And we're going to talk about why it's more safer to follow the 18-degree solar depression angle. Okay, so if this is a 24-hour clock, this is night time. That's when the sun is 18 degrees below the horizon. And this is when twilight starts. This is when dawn, the crack of dawn, starts. And it carries on until the sun's solar disk pops above the horizon. And then that's it. You can't pray Fajr no more. That's at its highest point. Just past its highest point is Dhuhr, and then again mid-afternoon, Asr, and then when the sun's solar disk completely disappears below the horizon, Isha, and then you get twilight, Maghrib, and then you get twilight, and then you have Isha. So how is the time for Fajr determined? We have an ayah of the Quran. And eat and drink until the white thread of dawn appears to you distinct from the black thread, darkness of night, then complete your sawm. So the black thread, the black thread of darkness from the white thread of dawn. So as you get first light khalas and you get the light spreading across the atmosphere, that's the time of Fajr. So it's visible at the crack of dawn. So that time is visible at the crack of dawn, and a white light that appears ghalas and spreads across the horizon is far. The Prophet ﷺ said the time for the morning prayer is from the rabu of dawn until sunrise. So twilight. So why is twilight important? Twilight is the time when your sun goes below the horizon until complete darkness, and when from the crack of dawn till the sun shows itself above the horizon. That's the time that's twilight. It's neither completely lit, nor is it completely dark. The sun itself is not directly visible because obviously it's below the horizon. Let's drink some water. All right. If we didn't have an atmosphere on the earth would be completely dark. The minute the sun went below the horizon, you'd get complete darkness, like it is on the moon. It's because we've got an atmosphere that, even though the sun is below the horizon, the light is still hitting the atmosphere and it's being refracted and reflected and scattered across parts of the earth still for some time. So that's the reason why you still see twilight when the sun's gone down. Twilights are very beautiful, as you know, and straight after sunset, the sun's about to go down, the sky becomes red, and as twilight descends, as the sun's solar angle depresses further and further below the horizon, that changes to white, and ultimately it'll disappear. So what time does this happen? This is where the problem lies. There's many definitions of twilight. There's civil twilight, when the sun is 6 degrees below the horizon, nautical twilight, 12 degrees, and astronomical twilight at 18. So here's the horizon, here's the sun. So from here to here, 6 degrees is known as civil twilight. This is the time when in England, by law, they switch on the street lights. And half an hour after the sun goes down, they start to lock the parks and public places. And once the street lights come on, it gets darker than it normally should be anyway. But you can make out a few stars, it's getting dark. From 6 degrees to 18 degrees nautical twilight. Now, Just at the end of nautical twilight, this is when seamen stop observing the horizon and taking measurements, because they can't differentiate the horizon from the sky anymore. So it's kind of dark, it's very dark now. But the last part of the light is still visible in the sky. And if you are in a truly dark place, you'd see that the sky is actually this color. Moving on to black now. And that's from 12 to 18. And total darkness, I think when it's the lux levels are 0.00006, is when it's complete darkness. And one really surefire way of working out if it is complete darkness without having a clock is to observe. If you know your constellations, you know your objects in the sky. Now the very faint objects will not be visible until the sun is 18 degrees below the horizon. So if you can't make them out and you are in a dark sky, then you know that it's not Fajr. And you've got to wait till you can see them clearly to know Isha, that you know that it's Isha. Okay, so here's the angle of the sun from the horizon, the light levels, and 15 degrees it's more or less dark. And then you carry on to 18 degrees, and at 18 degrees it really gets dark. So twilight. So what twilight do we follow for Fajr and Isha? Most Islamic astronomers and academics agree in twilight being 18 degrees below the horizon. Abu Hanifa advocated 18. The two Imams advocated 15. Now, 15 degrees between 12.5 and 16 is where you get the red twilight, Shafaq al-Ahmar. Now, once the redness disappears, according to the Imams, you can pray. But Imam Abu Hanifa says, no, it's 18 degrees, we have to wait till the white disappears as well. In England, we follow the 18 degrees, and I'm going to tell you why we do that. It's not something new, it's something that's been in existence for 1,000 years. And the ulama in the past used it, our astronomers used it. And here's a chart of all the astronomers, polymaths and academics that advocated 18 degrees and above. Very famous names like Al-Batani, As-Sufi, Biruni. 18 for Fajr. And actually some of them go down to 19 and 20. So if you think 18 degrees is dark still, then what light are they seeing? And then Isha again, 18 degrees, 17 degrees, 19, and 1 or 2, 16. So it's more important to worry about your Fajr than it is Isha, because from the ayah in the Quran. So you can see that nobody advocated solid depression angles of less than 18 degrees below horizon. So Allama Shami rahmatullahi alayhi advocates 18 to 19 degrees as the time for Subh Sadiq in his celebrated book Rad al-Mukhtar. Allah Hazrat Ahmad Raza Khan rahmatullahi alayhi in his Fatawa Rizviya, and this is a whole book he's written on the phenomenon of Subh Sadiq, on this issue of solid depression angles and twilight. And Maulana Ashraf Ali Thanvi in his Imdadul Fatawa, again 18 degrees. And Sheikh bin Baz of Saudi Arabia, along with Sheikh Fawzan and the shura they have. In one of their decrees in the Muslim World Degree Center, 19 Rabiul 1406, they said Fajr corresponds to when the sun is 18 degrees below the eastern horizon. So Imam Abu Hanifa rahmatullahi, Subh Sadiq and Dusk Shafaq, these two occur at the same time when the sun is 18 degrees below the horizon. Abu Rayyan al-Biruni, a very famous Islamic astronomer, polymath, he writes again when the sun is 18 degrees below the horizon. Mufti Azam Baghdad, Allama Muhammad al-Usi, again 18 degrees. And in 1983 in England, we had a convention, because in England, as you know, we don't get it's very cloudy for many months of the year. Most of the year, actually, especially up north, it's cloudy. We can't detect Fajr times properly, or Isha times, or moon times for that reason. So we've always been shrouded in controversy, and we've had problems from the beginning regarding moon sighting and regarding Salah times. Why? Because most of our skies are always cloudy. So in 1983, we had an agreement, the ulama had an agreement where they all agreed that we were going to agree. Some of the most ulama in England were there, and from India and Pakistan, and it said that Subh Sadiq is when the solid depression angle is 18 degrees below the horizon, and likewise for Fajr, for Isha as well, when the sun goes down. So Sayyidina Aisha, this is a very interesting hadith to understand. So Sayyidina Aisha says, we the Muslim women would attend the morning prayer behind the Prophet ﷺ with our bodies covered in sheets. After the prayer, when we would return home, due to the darkness, al-ghalas, the word used, very important, we could not recognize each other. Hafiz ibn Hajar al-Asqalani writes, due to the darkness we could not recognize each other means due to the darkness they could distinguish the form of a body but not recognize whether it was Khadija or Zainab. Now, being in Saudi Arabia, you know that they're very generous with their salah times. Isha can be from anything from 15 to 20 minutes, Fajr, from 15 to 20 minutes long. Now, if they pray on the crack of dawn, or straight afterwards. Now, when you go into prayer and you come out, it's still dark. At the time of Rasulullah, the prayer must have been a bit more generous, right? We know from hadith that do not prolong your Fajr prayer too much, but compared to the other prayers, it's longer than our prayers is today. Now, they would pray and they would come out, and even after praying the prophetic prayer and coming out, they could see each other, they could see the silhouettes, because it's possible to see a silhouette in darkness, because the sky behind you is always going to be brighter. Even when the sky is totally black, it's going to be brighter than it is normally. But they would not be able to recognize the faces. So this is very interesting, because even after that lengthy prayer time, they could not recognize each other's faces, meaning the sun was very low down below the horizon. And it was still low down below the horizon when they came out. Now that could never happen if, like England, some prayer times put the sun at 12 degrees, nautical twilight, or 15 degrees. This had to be 18 degrees. So al-ghalas is translated as the last part of the darkness of the night that separates, which is joined to the first light of the day. So the darkness joined to the day, that distinct moment, ghalas. And it has to be dark. Yeah, it has to be, it has to be completely dark when you're seeing that. So Dr. Ilyas is a famous Islamic astronomer and scientist from Malaysia. He's got a very famous book called Islamic Astronomy for the 21st Century, something whereabouts. And even he mentions, without reading the whole thing, that in modern times astronomical twilight has come to me. So they understand that it's astro-astronomical twilight. So the phenomena, astronomers acknowledge that, because the only people that are really concerned with 18 degrees solar depression angles are astronomers, because it affects their sightings of celestial objects. And the only other people that are concerned are ourselves. So they understand that they've given it the term astro-Islamic twilight. Indeed, 18 degrees solar depression was a commonly used value for Fajr and Isha in the medieval period, when it was based on careful observations. Nevertheless, slight variations, again, variations from 16 to 20 have been observed. But for twilight, the variations are, as I'll prove to you, it's from 17.5 to 19.5. The 16 degrees is not astronomical twilight, but you're moving back, you're moving earlier for your Isha times. Whereas 19 degrees and 17 degrees were the parameters, as I mentioned. It's the 19th for the Fajr, the Fajr, and the 17 for Isha. Astronomy of Islamic Times for the 21st Century. That's the name of the book. Right. This was an experiment that was conducted by scientists in Malaysia 4 years ago. It's from the International Journal of Applied Physics and Mathematics. Now over here, they're giving you the time, and they're giving you the altitude of the sun, and they're giving you these are light quality testers. They tell you how dark the sky is in the sky. So SQM meters and the altitude of the sun. So even when the sun is 18 degrees below the horizon, it's still registering light. You can see that it's still registering some light in the sky. And this was calibrated within the parameters of the human eye. So this is basically, it's not a very superfine instrument that's picking out light that you and I cannot see. It's calibrated to the same parameters as the eye sees. So what this is seeing is what the eye technically can see. Now again, if we look here, this is the horizon, 0 degrees. So the sun is gone down. This is the time for Maghrib, official time for Maghrib. And as the sun moves down the horizon, 10 degrees, 15 degrees, 20 degrees. See, this is the disappearance of Shafaq Abiyad. So this is the disappearance of white twilight. At what degree is that? It's looking like it's 19. It's very close to 20. This is the time, official start time for Isha. So we start Isha about 2-3 minutes afterwards. But they proved that it's 18 degrees and beyond where you get complete darkness in the sky. So various organizations in the world. We have the University of Islamic Sciences in Karachi, 18 degrees for Fajr and 18 for Isha. That's followed by Pakistan, India, Bangladesh, Afghanistan, parts of Europe. ISNA, 18 degrees for the USA and parts of Europe. Muslim World League, 18 degrees and 17 degrees for Fajr. Europe, Far East Asia, parts of the USA. Al-Qura University in Mecca, 19 degrees and 90 minutes after Maghrib and 1:20 during Ramadan. I suspect the 1:20 is to give people more time to get into the mosque for Isha. This is in the Arabian Peninsula. And the Egyptian General Organization of Surveying, 19.5 and 17.5 respectively. So they're actually playing it safe, or they've got the data on hand that proves that even up to 19 or 19.5, as we proved from the previous scientific study, that it's still technically Shafaq al-Abiyad, the white twilight is still visible. Not to you and I in cities, but out in the country or above the sea, it's still visible. So persistent twilight, what if the sun does not set low enough to ever go back? Sorry, just one thing here. You know the Al-Fajr Islamic clocks you have, or any Islamic clock you get, or the watches you get, if you look in the instruction manual, or even in Salah times, if you were to go to the internet and find a prayer timetable, and it would have, you can actually choose your solar depression angle, or you can choose which university you want to align yourself with. So depending on the university, this would actually give you the times for prayer times according to the angle of the sun below the horizon. I used to choose University of Islamic Sciences, Karachi, but now I just like to put 18 in. Persistent twilight. What if the sun does not set low enough for the sky to ever be black? What is the ruling on prayer and fasting? What happens to the night prayer, tahajjud, and God's mercy? Now, in England, in the summer months, from the 21st of May till the 20th of July, we have what's known as persistent twilight. This is where the sun doesn't descend 18 degrees below the horizon. So technically, it's not dark. If it's not dark, how can you pray Fajr, and then how can you pray Isha, and how can you pray Fajr in the morning? Because to pray Fajr, it needs to be complete dark, and then the darkness needs to separate, the whiteness needs to separate, and that's Fajr. So many events, we know that in the last part of the night, the mercy of Allah subhanahu wa ta'ala descends, and He descends to the lowest part of the heavens and says, ask of me and I shall give you. Who is there to seek refuge in me? So if that doesn't happen, does this still happen? Laylatul Qadr, starts after Maghrib up to Fajr, and your tahajjud prayers. So what happens? Do they still happen? Do they not happen? Rest assured they do happen, and I'll explain to you how. So from latitude 48, which is somewhere in France, and above, which is, if you know where France is in the world, that latitude, I think it's midpoint, just below France. Latitude 48 and above, the sun never descends 18 degrees below the horizon for some parts of the year. Now London is at 51 degrees 34 seconds, or is it minutes? 51 degrees. From the 22nd of May till the 20th of July 2012, in London, the sun will not descend 18 degrees below the horizon, which means you've got perpetual twilight. You've got a problem with your Fajr and Isha times now. Bradford is north, higher up. It's at 53 degrees. So from the 12th of May till the 31st of July, so it's even more days. The 22nd and the 12th. And it's longer this way as well. So how does this happen? Well, basically, the Earth rotates around the sun in 365.25 days. That's approximately 5 hours, 48 minutes, and however many seconds. Now, we've always been told it's 365 days. It is. But it's actually a bit more than that. It's 5 hours more than that. And it's important to know this because you'd find out when we work out the prayer timetables why it's important to know it's actually 5 hours and not just 365 days. It also rotates around its own axis every 24 hours. So not only is the Earth, let me show you here. So this is the Earth. So it's rotating once on its own axis in 24 hours. Yeah? So you have a day and a night in 24 hours. And also it's rotating once every 365 days around the sun. So every 365 days, it does one complete rotation, one orbit around the sun, and once every 24 hours, it does a rotation on itself. So the Earth, it's got a tilt of 23.5 degrees. So as you can see, the Earth is not straight. It's not like this. It's actually tilted 23.5 degrees. Now this is what gives us the seasons. I'll explain to you now. So when the northern hemisphere is tilted towards the sun, we get long days with short nights. And when it's the southern hemisphere is tilted, we in the north are going to get shorter days and longer nights, and they're going to get longer days and shorter nights. I'll explain to you. Right, London, 51 degrees. That's where we are. So anything above 48, which is going to be about here. Yeah, it's halfway through France. 51 degrees and above, you get, well, from 48 degrees and above. So at the 48th parallel and just above, you're going to get one day in the year where you're not going to get perpetual darkness. You're going to get one day of twilight. As you move up, you're going to get 2 days, 3 days, 4 days, 5 days, and it carries on. When you get to England, you get 2 months, and as you carry on, Scotland 3 months, and you carry on past the Arctic Circle, and when you get to the North Pole, you get 6 months of perpetual daylight where the sun doesn't descend below the horizon, and in the winter you get 6 months of darkness where the sun never rises above the horizon. So the Muslims in Norway, Sweden, Denmark have a big problem. If you think we've got it bad in England in the summer, what do those poor guys do? Right, so this is the axial tilt of the Earth. So the Earth is tilted 23.5 degrees. It rotates once around itself. This is the ecliptic. This is where the sun is. The sun and all the planets are on the ecliptic. But we are not aligned. From the horizon, you wouldn't be aligned directly to the ecliptic. You'd be up. Your horizon, your celestial equator would be above you. So you can technically see that from any point in the world. So, okay, do you remember, right now I mentioned the northern hemisphere, southern hemisphere. So here, okay, imagine this is the sun. Okay, imagine the sun's hitting us here. So now this is the Earth, this is its angle, and this is how the Earth goes around the sun. So if the sun's over here and the sun's hitting directly here, you can see that the part that's getting the light is this part here. Yeah, the top, it's being deflected. Yeah, so the sun is hitting full on in the southern hemisphere. So you're going to get long days and short nights, whereas here you're going to get a very short day and a very long night. The Earth goes around the sun 6 months down the line. So this is June, July, August, September, October, November, December. Well, actually, it should have been December. Should have been for the north. Yeah, it's correct. Yeah, the northern hemisphere. Actually, December should have been here. So December's here. Now, actually, what's happening here? The northern hemisphere, okay. If the sun's here, this is June. The northern hemisphere is facing the sun. So the sun's hitting England full on, you can see. So we're going to get very long days and very short nights. So June, July, August, September, October, November, December. Now the Earth is on the other side of the sun. Because of the axial tilt, the Earth is facing, the northern hemisphere is facing away from the sun. So you're going to get the southern hemisphere hitting the sun. So you're going to get direct head-on light, longer days and warmer days. And the light is being deflected from us. We're going to get longer nights and shorter days. Hope that made sense. Here you can see, again it's the same thing, right? So if the sun's here, it's facing the sun, and these are the this is the equinoxes, the spring and autumn equinox. So when the sun is when the Earth is in March and in September, I think it's 21st March or 23rd March, and again equally 21st or 23rd September. This is when you're facing, the Earth is facing head-on to the sun now. So it's not, the northern or southern hemisphere is not at an angle, it's actually facing head-on. So you're going to get an equal day. The night and day will be equal across the whole world. And then as you move, whichever whichever hemisphere faces the sun more, the days will start to get longer, the nights will start to get shorter. Does that make sense to you? So again, you can see the angle of the tilt of the Earth in July, the northern hemisphere, you get northern summer because it's facing the sun. As it travels around, now the Earth is facing head on to the sun, equal days. As you carry on, we are facing away from the sun. The northern hemisphere facing away from the sun, southern hemisphere is facing the sun. So the southern hemisphere is going to have its summer, we're going to have our winter. Shorter days, longer nights. Because for large parts of our 24-hour day, we are facing away from the sun. Okay, this is an animation of that. This is the winter solstice. So this is where basically the Earth is the northern hemisphere is facing away from the sun. So if you look here, you can see that this part, we'd be about here somewhere. So can you see the Earth, the sun is illuminating the southern hemisphere. So the northern hemisphere, can you see it's still dark here? This is where the sun never rises. And here, if the sun does rise, it only rises for a few hours before it sets again. But here, you've got a massive day, look. Very, very small light and a massive day. And over here, it's perpetually illuminated. You can't see it here, but it's perpetually illuminated. It's your day, 6 months of day. Mind you only get the 6 months at the poles. You hear this thing? Okay, so this is a polar day now, right? The sun rises, and it never rises really high above the sky. It just travels across the horizon, and it sets. So there you go, look, 2:45 and it's Maghrib already. So it's night from 2:45 all the way till, what would it be? What time was it? 9, 10 o'clock when the sun rose? Okay, this was taken by National Geographic in Alaska, right? This is a polar summer. So as you can see, the sun is descending, and it doesn't hit the horizon, and it rises again. Where is the sun? Here or here? This is the sun, right? There's the sun rising. And this is the highest point it gets in the sky before it starts descending again. So that would be your Dhuhr. Here would be your Asr. And your Maghrib should have been where the lowest point was before it hit the horizon. It would just go back up again. Actually, I can So if you see the sun's going down, so your Maghrib would be about here, there. It didn't hit the horizon, it just went down and went back up again. So you're going to get this for 3 or 4 months. Depending on how far north you are, you're going to get this. This actually would be for a very short duration. Because the sun's actually rising quite high above the horizon, which means that it's not going to be that, Okay, this is the winter sunset in London. As you can see, because we're quite far north, the sun doesn't go from here to here. Again, it's at an angle. Can you see that? Right. So it's even setting at an angle. It starts here and it finishes kind of here, right? The gap of that much. Now, normally when you see beautiful sunset pictures and the sun going down, you see the sun going down from the top straight to the bottom. That's at the equator. But because you're so far north, the sun actually goes across. It descends like that. So what's wrong with the UK timetables? Well, it's a 3-part problem. There's a problem with the original mushahida, the original observations. Wrong times for Fajr and Isha. As a result of that, we have been praying. I think it's before 1987 when these guys did the mushahida. We used 12 degrees solar depression. Now, anybody that goes to a really dark sky in the sky, really like a boat sky, 0 or 1, will see that it's not dark. Yet in England, for like 10, 20 years, we were praying Fajr according to 12-degree formula. In 87, some guys did observations and they drew their own timetables. There were massive problems with that, glaring errors we're going to go into. Now, no consideration for certain scientific principles, e.g. elevation, atmospheric refraction, or how to even observe properly. Now, for a scientific experiment to be sound, it must fulfill all conditions associated with it. So for anybody to tell us today that these are our mushahada timings, we observe the sun rising and setting at this time, we saw twilight dissipate at this time, they've got to fulfill certain rigid criteria. If they don't fulfill that, well, your observations are flawed. Now, you've got to state your goals. You need to know what you're going to do, your assumptions, your DV and your IV, and your confounding variables. For it to be accepted as fact, you can't just do one-off experiment. You've got to replicate that, and if it's replicable again and again, and it brings you the same data, then that's a sound scientific experiment. If it's only a one-off, then again, you can't take that as scientific fact. So what's the DV in this case? What's your dependent variable? The DV is what is being measured, namely the darkness of the sky. That's what we're trying to measure. What's the IV? The IV is how you're going to measure it. Where you're going to go. You're going to use instruments. You're not going to use instruments. What are your variables here? Location, your method. What are your confounding variables? What could throw your whole experiment? Air glow, night glow, causes of light pollution. Okay, now, Hizbul Ulama, in 1987, a group of ulama from Blackburn, under the name of Hizbul Ulama, it's only 2 people, and to this day it's only 2 people, carried out observations to determine the exact time of Subh Sadiq. It was pioneer work, nobody's faulting their work, nobody's saying that, like they did a monumental work. These 2 guys, without scientific knowledge and the principles of observation, went out and with true niyas, decided to find out the time of Fajr and Isha for the Muslim Ummah, and their timetables have been used ever since then. Now, we're not faulting their niyas, but what we have to fault is how they did the observations and the times that they produced. The times, again, like I said, these times have been used for the whole country. They conducted personal observations between September 87 and August 88 in Blackburn. However, they made several errors. First of all, only 97 successful observations were performed, consisting of 34 for Subh Sadiq, 27 for first light and 7th Tayyibun, the latter limited to summer, 62 for Isha, 22 for Shafaq Ahmar, and 40 Shafaq Abiyad. So for the whole year, only 98 successful observations. To create an accurate timetable, you need 4 observations daily. Subh Sadiq, Subh Qadib, Shafaq Ahmar and Shafaq Abiyad. This would equate to 1460 observations. So Hizbul Ulama have only carried out 98 for the whole year. The rest of the gaps were filled in through assumption. Okay, there's a 2-minute difference here, 2-minute lag time here. Okay, it follows on sequentially. Okay, so we fill the times in here. This is the Mushahada ke mutabik waqt fajr. This is the original observation report. Now, I'm not going to kind of criticize their work severely, but just go into one thing. So the 21st of May observation, Fajr, first light was 2 hours 22 minutes. Right, the time for Fajr they recommend, the time for Fajr is 1 hour 32 minutes. Recommendation, Fajr, 1 hour 51 minutes. So first light is at 2:22. Their recommendation for Fajr is at 1:51. Discrepancy, 31 minutes, Tayyibun 19 minutes. So that's the very first thing. So they're observing Fajr at a certain time, they're recommending you pray Fajr at a certain time. And what they did is they've got funny things in their timetable. They've got, if you live in London, you add on this many minutes. If you live in Preston, you add on this many minutes. Where did they get this from? I mean, you can't do observations for one location and produce timetables for another location based on the observations for that location. And this is what they've done, and their timetables are we've been using these since 1987. So these two guys, they took a few people that were with them to observe. Now, one of them was Maulana Ahmad Siddharth, and he himself says that I didn't know what was going on. He says he showed me Subh Sadiq. I just happened to be present at Haji Adam Patel's house at those times. So when these guys were trying to work out the times for Subh Sadiq, they took along Maulana Sahib and they said, Maulana Sahib, come, this is Subh Sadiq. Can you see it? And he's saying actually that I didn't know what was going on. We went to where the present Asda is. The present Asda in Blackburn town, in the middle of town, they're trying to observe Fajr. I mean, anybody with any astronomical knowledge knows that you never do a celestial observation in the heart of light pollution. Qadi Ghulam Ahmad Patel, again he says, at the time I'd been in the UK for 6 years and used to spend a lot of time at his house, at so-and-so's house. And Maulana Yaqub Muftahi, he's the guy who did the observations from Hizbul Ulama. Now, he took him, Yaqub invited me to join them as well. This happened on 5 occasions. At one time, the late Maulana Ilyas, Imam of Leytonstone Masjid, was present as well, and he also joined us. At that time, I'd only been in the UK for 6 years and didn't know anything about Subha Sadiq. So he himself is saying that this phenomena, Subha Sadiq, I don't know how to observe it, I don't know anything about it. I just happened to be at Hafiz Saab's house, and we ended up doing the observations. So these two guys have washed their hands off these observations as well and said, we don't take no credit for this, we don't know what was going on, we didn't know how to observe, we have no knowledge of this science. These errors of Hizbul Ulama timetable came about due to a lack of knowledge with regard to the nature of Subha Sadiq. This is a fatwa signed by Mufti Taqi Usmani in December 1990. Now, once these guys produced these timetables, they gave these timetables to like fiqh councils and bodies. And it's only when you get your timetables authorized by a higher authority than yourself can you use them. So they went to these great personalities in Pakistan, the University of Islamic Sciences, Karachi, and says, look, Mufti Saab and whoever, these are our timetables, can you give them the seal of approval? And even then, Taqi Usmani said, no, we can't use these for the country. Okay, observation mushahadah that took place in Blackburn are not acceptable for the rest of the UK. Again, in Mufti Ismail Barak Ad-Darami's in his Fatawa, Darul Kanderia district, Baroch in India, again they're saying that we can't use these timetables. Hizbul Ulama, altogether 31 days of observations were not done, so 315 days out of a year, no observations. And a whole 3-month gap was observed in one of the observations. So like for January, April and July, no observations. Out of 50 observations, only 11 days were actually recorded. So only 11 days were put down on paper, the rest of them weren't even put on paper. This is not scientific inquiry, and it's certainly not doing justice to the science of ijtihad. Their own times do not match what they have recommended to people. Observations for the 15th, 21st, 25th, 6th June, 13th June do not match the times they've given to the masajids. The very limited non-scientific observations have no credence and furthermore can't be used for the rest of the country. They've never come to the table. Now these people have been asked, people have done mushahidah after them, and they've said to them, sit down on the table because our times are, what we've observed is different from what you're showing us. So come and sit with us, let's find out what the problem is, and let's see where we can come to common ground. They've even refused to do that. They say, no, our timetables, they've been accepted. Everyone, even in America, they're known. Shaukat Khurshid, the guy from moon sighting, he kind of is a great supporter of these times, and if you go on his website, he gives these times. And they say, no, these have been used everywhere, we're not going to revise them, there's nothing wrong with them, and they in fact give you some kind of pseudo-scientific evidence saying, no, our times are correct. Recent observations done in Preston confirm that first light. Now, Wifaqul Ulama, this is a group of ulama, for the last 4 or 5 years, they've been lobbying mosques in and around England to change their times, and they did their own researches. They went to the north, the east coast and west coast for Fajr and Isha respectively, and they did the observations for Subha Sadiq, and they came to the conclusion that it's 18 degrees. Now, the SF Subha Sadiq by Maulana Shabir Ahmad Kalakhil, this book gives the findings of scholars again from Darul Karachi. This was also done in Karachi. Ulama in Karachi did observations, and their findings are recorded in this book, and again it was 18 degrees. Imam Ibn Abidin Ash-Shami writes in Murad al-Mukhtar, it is fard obligatory for every person to know the injunctions that apply to his everyday life so that he can avoid falling into haram. So basically for you and I, we need to know. It's fard to pray, so we need to know, we need to make sure the conditions that are attached to the prayer are sound. If our conditions are not sound, there's no prayer. If you don't know the time for Isha and you pray Isha, even if you pray Isha on speculation that maybe it's Isha, maybe it's not. If you're not sincere in your heart, if you're not sure it's Isha, then if you were to pray, it wouldn't be Isha. So it's one of the prerequisites that for the prayer to be valid, one needs to be sure the time for prayers has started. Our ancestors, now for Mushahidah, what's very important to understand is our ancestors had very acute night vision. Now I remember in Pakistan, like in the village, like I used to walk around in complete darkness with farmers, and I never knew where I was going, but they could see where they were going. And the skies in Pakistan are both skies of one. Myself, you could see like thousands of stars, and you could see the Milky Way. You could make out all the major constellations. I had no problem seeing anything. And these guys, on total moonless nights, when it's very, very dark, these guys could see where they were going. Community sittings versus single bar needs to be set somewhere. Also, another thing is that imagine you've got a group of 10 people in this village. You've got 5 old men and 5 young men, and they're waiting for Fajr. Okay, they're waiting for Fajr. The young men and children detect ghalas at X time. But the old people say, no, actually, we can't see, we're going to wait, we can't see, it's still dark, your opinion, your kids. What do? You've got to set the bar somewhere. So the most acute vision amongst you, there may be somebody in your community that can see Subha Sadiq without timetables and without clocks. So then you have to you need to set the bar and realize that what degree is that? It's 18 degrees. Now, if the majority of people in the cities cannot see sunset, time for Isha at 18 degrees, well then that's because there's defects. There could be defects with your eyesight. You could be a smoker, light pollution, your age. But you've got to set the bar somewhere. You can't have it subjective. But when you're on your own, if I was in the jungle, if I was in the desert traveling on my own, then obviously it would be subjective. Whatever time I saw the sunrise, the time I saw ghalas, I would pray. But you've got to set the bar for the community. So you've got to print timetables, and you've got to have, this is the time, 18 degrees. Personal mushahidah. Now, people go out, some people have done this, they've said, well, we looked out, brothers in Birmingham did it, they made mistakes in the observations. I looked at the sky and it's still dark, so it's not Fajr. Well, actually, no, that's incorrect. Do you even know what you're looking for? It takes 20, that's taken from Wikipedia, but it actually takes 40 minutes to several hours for your eyesight to become used to complete darkness. Amateur astronomers use red torches to view papers. Right, so even amateur astronomers, I remember, where you have like red torches. You put a dark red cap on your torch, so if you illuminate your papers, it doesn't destroy your night vision. It doesn't degrade your night vision. Magnitude star test. Now, most people that do mushahidah, have they done a magnitude star test? They can't even see stars, let alone do a star test. So then how can they possibly say, yeah, we've done mushahidah for the time of Fajr? Now, Maulana Ashraf Ali Thanvi says in his book that you need to be familiar, you need to have experience, right, of Subha Sadiq. You need to know the science. Without the science, there's no way you can identify Subha Sadiq. Right? Now, one way is get into the habit of sky watching and get to know the sky. If you ask most people today, where is the Big Dipper, the Big Bear, the Small Bear, right? Where is Orion, the constellation? Where is Andromeda? Where is the Milky Way? Have you seen the zodiacal light? They will say, sorry, what are these terms? Let alone have we've seen them or not. Because we simply can't see the sky no more. So it's a good idea, day in, day out, to be familiar with the sky. I could be observing for 2 weeks and think I know the sky. And then, I can see the constellations. I think I'm ready to do a nighttime observation to see the time of Subha Sadiq. But yet, maybe somebody keen like yourself who's been doing it year in, year out will know, hang on a minute, those constellations don't look as bright as they should do. That particular star, it's not as bright, it's not as haze-free, or it's hazy, as it should be. So for you, you're thinking, hang on a minute, something's not right about the sky, because you know the sky, right? You know how much light is still dissipated or not dissipated. Whereas I won't be able to make that judgment. So part of our problem is we don't even know the astronomical sciences no more, and we don't know our sky. The third world has very dark skies. The first world, we have very bad skies. We can't see stars. So technically, you either need to go very, very far, like 100 kilometers out of town, or preferably be on a boat in the ocean, or go to the third world to get a truly dark sky. A few important things to factor in: knowing exactly what you are measuring or looking for. Right? Stuff like light pollution, moon, this will affect your observations, air glow, knowledge of the zodiacal light, Geigenschein, aurora, glare of big cities, eye adjustment times. So here you've got a map of England. It's an artificial map of light pollution. Now look how bad light pollution is in England. Right, the red parts correspond with very bad light pollution. I think it's bought skies. So even along the edges here, you're not going to get complete darkness. It's a bought sky of 1. It's only in the sea where you're going to get true darkness. So those guys did observations in the Midlands here, right, where you get the worst possible skies. This is the sky of Europe. Look how bad Europe is. So technically there's nowhere you can do observations. I mean, Eastern Europe here, you're going to get better skies. But Western Europe, forget about doing observations. This is a map, a nighttime map of light pollution. It's Europe, England, America. But what really surprised me when I saw this map is look at India. Look at parts of Indonesia, and look at this is the River Nile, right? And that's like most of the population lives by the River Nile because of cultivation. The rest of Egypt's a desert. So over here, look at the light pollution, and we're on the west coast of Saudi Arabia. We're down here, Jazan, and as you know, this part's not that developed. Most of Saudi Arabia is not developed, but this part is not developed. And look at the light pollution. Some of the worst light pollution in all of Saudi Arabia is where we are. This is Abha, Khamis. So yeah, I've seen the light pollution there. But here, look how bad it is. Look at India. Positively shining. Iran, Pakistan. This is the border area of Pakistan. These are mountains. Right, scientists estimate that only 1 person in 2 will ever see the Milky Way. Have you ever seen the Milky Way? I only ever saw it once. So in 1993, that was the condition of our skies. In 2000, they had gone worse, and obviously 2012, you can only imagine how bad they've gone. So these areas are true darkness. Everything else, you can't really do justice to observations. Star count tests. Now, there's been an ongoing star count test in England for a long time at the moment. It's where you look at the constellation of Orion and you try to work out how many stars you can see in that constellation, and that shows you how bad your sky is. So in 97, these are the people. So in London, you could only see fewer than 5 stars. As you move out, it's less and less, but over here again, it's 5 stars. But look at that. Look what's happened since 2007 to 2011. Only 4 or 5 years. Look at that light pollution that's appeared over here. It's increased in London, it's increased over here. Now Orion, I remember 20 years ago, I could make out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 plus stars of Orion. I could easily make out, right? About that much. Which technically it may be possible to see 20 years ago. But now, I can barely see Orion from my house. So almost 1,000 people in different locations around the country took part. Participants were instructed to pick a clear night to count the number of stars in the constellation of Orion. Fewer than 1 in 10 said they could see between 21 and 30 stars, and just 2% of people had truly dark skies seeing 31 or more stars. So if you've not got a truly dark sky, how can you even attempt to do mashahida for Fajr? You're not going to be doing a service to Islam if you do try. Right, this is the constellation of Orion. So you can see the shoulders. Here's the skirt, and here is leads to Sirius, and this is the dog star, and it's supposed to be Orion the hunter with his dog, and this is the belt, and this is his sword. This second star here is the Orion Nebula. It's a beautiful nebula that appeared in the medieval period. It was a star that blew up. It was a supernova. The Chinese recorded it, and it's the birthplace of many new stars at the moment. We've observed hot new developing stars there. It's only been around for about 1,000 years, so it's still very, very new. Right, there's the constellation Orion. Can you see that? 3 stars, and that's the middle star. It's hazy. If you get a truly dark night, you can see many, many stars in the sky that are not going to be pinpoints, they're going to be hazy. That's because they're not stars, they're galaxies, nebulae, objects. Galaxies, the arm of the Milky Way, it's kind of hazy. But we never see that, you see. We just see a few stars as pin drops, and they're not even twinkle. That's how bad our stars are. So you can get involved in this project if you go to this website. The BBC ran a report on it. That's the website. And if you want to get involved, you can get involved by going to this website. Okay, it was made by a person called Bot. It tests it's a chart. By looking at, you can determine how dark your sky really is. Now, if you've got a really, truly dark sky, your limiting magnitude, this is the extreme of human vision now, is 7.628. On average, in a dark night, the average person sees up to magnitude 6 stars. In London or in a built-up city, you're lucky if you can see a magnitude 4 star. So you should technically be able to see the zodiacal light, Geigenschein, the zodiacal band, which follows, the zodiacal light actually isn't, it's not just the light, it follows the ecliptic. It's dust, interstellar dust on the ecliptic plane. So you can actually follow it to the Geigenschein. You should be able to see that. M33, M31, this is a galaxy. M31 is Andromeda galaxy. You should be able to see these galaxies with the naked eye. Objects, Scorpius, Sagittarius. Sagittarius is in the heart of the Milky Way. And it casts shadows. So all these objects collectively will cast a faint shadow on the ground. You'll see the air glow. The air glow is visible above the horizon. So imagine putting there's the horizon and you've got your fist out on the horizon. About the top of your fist, you should be able to see a faint band of green light. And it gets thinner and thinner as you look up. And on exposed shots, it comes out really well. And this is the natural glow of the atmosphere. This is excited ions and stuff in the atmosphere, aerosols, that give off a luminescence, chemical luminescence light. Now, Jupiter and Venus are going to be so bright that if you were to look at Jupiter and Venus, you degrade your eyesight. That's how bright Jupiter and Venus really are. So, a typical truly dark sky. So if you were to go out of London, say by 30 miles, and you were in a field, your sky would be about this one. You'd be able to see these 17 stars that bear stellar limitation magnitude. Okay, this is with the telescope. 7.1 to 7.5. Again, you'd see air glow. You'd see M33 easy. I think it's the Catherine Galaxy or the Catherine Royal Galaxy, I think they call it. You see the Milky Way. You'd see the zodiacal light again. Again, you see shadows. Right? You'd see many Messier globular clusters. So you could see astronomical phenomena. So as you move down, when you get to kind of where we are, suburban skies, urban skies, the entire sky has a greyish, white, yellowish hue. Right? It's got a yellowish hue, and the Milky Way is invisible. M31, which is that famous Andromeda galaxy, is invisible. M33, M44. M44 may be glimpsed. I've never seen it. And you possibly, you won't see much. So here's an example of skies. So excellent dark skies. So if you've got a truly dark night, these are the objects you should be able to see. So as well as seeing stars, you'd see galaxies, you'd see other phenomena, you'd see meteorites, cross shooting stars, they call them. You could see satellites. And this is a rural sky and a suburban sky and an inner city sky. So look how the sky becomes more and more just blank. From seeing all the heavenly glory to seeing absolutely nothing. And you get this glow, like you get an ugly yellowish glow that I pointed out to you. So this is a truly dark sky. You can see the Milky Way band. And these are clouds. Now, in a truly dark sky, the clouds would form a light. The clouds, you'd see the clouds as black objects against the sky, because the sky is always going to be lighter than the clouds. But today, this is an average sky above a city. The city actually illuminates the clouds because there's that much light reflecting up into the atmosphere that the clouds will actually look black at nighttime, look white at nighttime. Right, this is an interesting shot. This was a picture taken in America, and that's a street light. And this is an exposed shot. It's probably been exposed for about 10, 15 seconds. That's a street light, and look, you can see minimal stars. And during a power cutout in that part of America, from the same location, subhanallah, truly, a sky as the ancestors saw the sky. You can see the Milky Way band. So that should be here, but you can't see it. And some of these objects, if you know what you're looking at, you know straight away that they're not stars. They're other things. So dark adaptation, the human eye reaches across 9 orders of magnitude. So the brightest and darkest light signal that the eye can sense are a factor of Rayleigh. That's a big number. At any one time, your contrast ratio is 1,000. That's because your eye needs to set at something that's dark, and it adapts to what it thinks is the darkest object. So from there to there, the contrast ratio is about 1,000. This can be shifted across 6 orders of magnitude, a factor of 1 million. Now it takes 40 minutes to several hours for your rods to adapt from bright sunlight to complete darkness. It becomes 10,000 to 10 million times more sensitive than at full daylight. Now, age, smoking, and alcohol degrade night vision. Now, during if I was a smoker, and say you were 60 and I was a smoker, and we both went out to observe. Now we know that after age 25, your eyes will start degrading. Your night vision is not going to be as acute as somebody who's pre-age 25. But as a smoker, my eye vision, right, is going to be worse than yours. If I am a drinker, my night vision is going to be worse than yours. Because what it is you're testing your eyes to the limit. You know, you are really like, it's become like a truly dark sky. It's dark when you sleep in Malaysia, Indonesia. I'm sure at night time when they switch the lights off, right, you can't see your hand in front of you, and you have to go sleep because there's nothing you can do, right? So you are testing your eyes to the limit, and in scientific studies we've seen that if you fire protons, subatomic protons at your eye, even one proton hitting your rods, your cells, it'll excite them. But you won't be able to compute, what's happening. It'll be irrelevant to you. It won't make a difference to you. But your rods have detected it. SubhanAllah. That's the cuteness of your eyes. So smoking, small things like smoking, can degrade your night vision. So that rules out any guys that smoke, whether you're young or old, to actually say, okay, let's go out and let's observe the time for Fajr, because you wouldn't be able to see Fajr properly. This is a small chart on the threshold. So as night kicks in, or you switch off the lights, the time to adjust. So your cones adjust in a matter of minutes, right? And then they kind of level out. But it takes a long time, right? 25 minutes. And here, actually, it carries on. It's about 30 minutes, 40 minutes. And for many hours afterwards, your sensitivity will increase by a certain amount of lux, point, whatever. But this is crucial when you're doing observations. The limiting magnitude, which is identified as being the magnitude of the faintest star near the zenith, right? This is basically a test that you do. So if you were to look directly at a star, you wouldn't see it if it was a very faint star. Like in astronomy, you look towards the left or right because your rods are there, and you can actually pick. And there's a way of doing it in astronomy, and then you keep looking, averting your vision, and your mind builds a picture of what you're seeing. So to truly know what level your sky's at before doing observations, you have a magnitude test that you can do. Because the eye at its upper limit, if you can see a 7.6 star, subhanAllah, you've got beautiful eyesight. There's 7,000 stars that are visible. 7,000 stars are visible, level 2 scales of darkness. Best possible skies are available on land. Don't know what that means. So here's another test, the Bortle test. Can you see all 7 of the main stars of Ursa Minor? Yes. And then you go on, and if you can get down to here, you have a truly nice sky. But in our case, no, we can't. So can you barely see M31 and Romeda? No or yes. Well, you've got really bad skies. It's not even worth you leaving the comfort of your armchair to do an observation, because you're not going to be doing any justice to it. So Ursa Minor, the dipper, as we know in England, that's Polaris. Now, if you know where Polaris is in the sky, Polaris is always in the northern hemisphere. It's kind of overhead, and if you know where Polaris is, you can never get lost, because judging by the ancients, used to use that as the directional star, right? The North Star. So this is Polaris. This is Ursa Minor. This is the visibility chart. So, for argument's sake, if you can see star 7, star 7 is of a visible magnitude of 4.2. That means your visibility magnitude is 4.2. So on the sky scale, you're somewhere in the middle, or towards the bottom still actually. If you can see star 19, you've got a beautiful sky. And eyesight, not to mention. So star 17 would be this star here. It's very faint. If you can see that, then you know that you're in a position that now we can observe the sky. Okay, so the zodiacal light, known as Subakadib, known in antiquity as false dawn. Now this is the picture of false dawn. Now it looks like, it actually looks like the time for Fajr. If you saw that in the countryside, and you said, okay, I'm going to wait for Fajr. Oh, it's Fajr. Right? You'd actually start your prayer, and you'd finish your prayer, and then that would become darkness again. And you'd think, hang on a minute, what's happened here? I've only observed this once in my life, and it was strange because I didn't know what I was looking at. I was observing the sky, and I happened to see this, and I thought, it's Fajr time, right? And it got brighter and brighter and brighter, and then it stayed there, and I knew from my clock that it wasn't the time for Fajr. And it just slowly petered out and disappeared, and the sky went dark. And it was kind of a strange light as well. It's a very eerie light to look at. It's a very strange light because it's not natural. It's not sunlight. It's actually reflected in planetary dust. So you get dust from comets and asteroids, and this dust orbits the Earth, right? Just as the Earth and Venus orbits. It's on the inside, the inner planets. And this dust, it's like we only get to see it. The best time to observe zodiacal light is in the equinoxes. Why? Because we're aligned head-on to the ecliptic. And the ecliptic is quite high up in the sky. And it's at the correct angle to reflect, the suns and the earth, it's just at the correct angle. So it reflects all that dust and you can see it. Right? Otherwise it's difficult for us to see. But if you're towards the equator, you're aligned by the ecliptic anyway, quite close to it. So you'd see it you'd see it more often. Can I have my hat? Okay. So this is a video now. This is a video of, if it does play. It's a sped up video of the zodiacal light. It looks like it's Fajr and then it's not. So air glow, what's air glow? At night time, the sky is never actually truly dark. Silhouettes can always be seen against us. So even if you and I went to the Arabian desert and you stood in front of me against the sky, I would make you out. Why? Because you would be darker than the sky behind you. Because of ion excitement at the upper atmosphere, aerosols and chemical luminescence. Effects can be seen by looking 10 degrees above the horizon. You remember I mentioned, look 10 degrees above the horizon, and you'd see, if you had a truly dark sky, you'd see difference in the color of the sky. You'd see a slight, very faint. When I talk about these colors, by the way, don't expect them to be super bright like you see in photography. You're talking very bland, very faint differences. Keen observers may think it's the time for Fajr because, oh look, we can see a greenish hue. This is night glow, air glow. Now, can you see these bands here? This is gravity waves, right? Air glow is part of the air, right? So as you get perturbations, as you get weather fronts traveling across mountains and rising and hot air rising and that, it causes ripples in the upper atmosphere, and that's what causes these. It's like it's the atmosphere is kind of fluid. So again here, right? So here you can see the zodiacal light rising, and there's the Venus, it's on the ecliptic. And if you look over here, you can see a greenness, slight hazy greenness, and you can see a gap here, green and a gap. That again is a disturbance in the air glow. Something's disturbed it, and it's become a gap now. So counterglow, Geigenschein. This is another phenomenon like the zodiacal light. The source of this is the same. It's the same planetary dust that's reflecting. right? But it's actually counter to the Geigenschein actually means counter. So it's counter, it's German, counter to the where the sun is. So if the sun is here below the horizon, it's going to be up there. Sun is here, it's going to be up there. Right? So it's 10, 20 degrees long and 6 and 8 degrees wide. So this is another phenomena. It's on the ecliptic. So basically, if the zodiacal light, the fake false dawn, if you had a truly dark sky and the ecliptic was quite high above, you could follow that band and it would join the Geigenschein. Because essentially the source for both of these lights is the same. These happen like tens of millions of miles out into space, by the way. So this isn't something that's happening so far away is affecting our weather over here. I mean, if you really studied the science of astronomy, you'd really appreciate the majesty of your Lord. And these are dust particles, right? Very small dust particles that have an effect so far away. Right, it's got stuck. Do you want to forward it from there? Press space. Press escape. Okay, now press. You know how to start a presentation. Put your mouse on top of that and press it. Here. Here, look at me. Andrew. Press that. Where your mouse is now, move towards the right by 4. Yep, this one here. Okay. So this is the Geigenschein. Okay? So this faint glow here is the Geigenschein. So you know the sun's here. Aurora, beautiful light display caused by the collision of energetic particles. Basically, the auroras are visible at northern climes, and they normally coincide with heavy sun activity. Every 11, you get an 11-year cycle where the sun has sunspot activity, and you get huge bursts of energy, of solar radiation that hits the Earth, and it's channeled in via the poles. You've got the Van Allen belts, magnetic belts, and it interacts with the atmosphere, and it energizes the eons, and I think it's ions. And auroras result from emissions of photons in the upper atmosphere, about 80 kilometers from ionized nitrogen. I think it's nitrogen causes the red glow and oxygen causes the green glow. That's what an aurora looks like, subhanAllah. And if you actually live in the northern climes, that's exactly what you'll see. Now, if you're observing Fajr above the sea, he's actually facing the sea. Would you think that's Fajr? If you didn't know what you're looking at, you'd think, oh. And it's so bright, it's causing shadows on the ground. Look, it's causing shadows on the ground. This was taken in Scotland, cloudy. Now this is an exposed shot. This is light pollution from a town. That town in the distance, look what it's doing to the sky. And that there, and again here. Now this is it here. Now if you were observing that, you'd think, through the cloud, I can see Fajr. This was taken this year in the UK. Again, look at that. Look at the light pollution, and look at the aurora, and you can see it. You can see it here. Again, look. You'd think through the cloud it's Fajr, and there again, light pollution there. But look over here. Look, it actually looks like it's the start of Fajr. The sky's blue, and the crack of dawn is green. Look at that, subhanAllah. That's light pollution again, and that looks like Fajr. But it's not, it's probably midnight, and it's just the aurora. This is an interesting shot. This was taken over York in England this year. Can you work out where the aurora is? The aurora light is? There. See, you need to look out for subtle lights in astronomy. Now that green patch there, very faint green patch, but if you're looking for first light, you may look at that and think, oh, through the cloud I can see Fajr. I can see the star of Subh Sadiq. Beautiful shot. Glackmore in Scotland this year. Beautiful shot. That's a railway. It's a road. Look how beautiful that is. That's that's light pollution, by the way, and that's the aurora. So look how ugly. I mean, even in exposed shots, look how ugly light pollution looks compared to the lights that God creates. Well, God's created the other light as well, but Fajr, aurora. Again, look. Okay, so now we know what objects we can mistake for Subha Sadiq. So once we know what they are, we know how to avoid them. So how are we going to go about actually doing mushahada? Well, travel as far away from the city as possible. Ideally, travel to the coast, right? So, or travel 20, 30 miles outside of a city in all directions. So you're in a total dark field somewhere. And even then, your sky is only going to be about, broad sky 1, not 0. It's preferable to go to the coast. Stand alone. You don't want a biased opinion. You want, if you're observing with people, you want somebody to stand in that field, you in that field, and you observe your observations separately, and you can tally up the times afterwards without bringing in bias into your observations. Let your eyes get used to the sky by constantly scanning the sky and averting your gaze. So you need to be there like 3 or 4 hours before in pitch darkness, just observing the sky. Don't let your eyes get light degraded. Keep observing the sky. Get to know the objects. Test the acute limits of your eye by looking at an object and averting it, seeing its brightness. With the averted vision, you'll see other objects that didn't exist there. Right? And as your eye gets more and more used to the dark, you'll see other objects appear in your averted vision that you couldn't see half an hour earlier. So try and spot the Milky Way, zodiacal light and planets. Look for meteorites and look for satellites. It's possible. I've seen them. You lie back on the grass, look up into the sky, and you'll see the odd stellar dust hit the upper atmosphere and burn up. And you can see satellites as well. Now, a way of seeing satellites is their orbit's different from the planets. Some of them orbit this way around the Earth, some orbit this way, some orbit that way, some are close, some are far. And as their panels reflect sunlight, you'll get like a blip. And they travel quite fast. Some travel slow, some travel fast. And you know it's a satellite. The way it's traveling, you know it's beyond, if you were to observe a plane, it's beyond that. And you know it's a satellite. And you can get maps. You can get sky maps and times of when a satellite will pass over a part of the sky. So if you can see these, then you know you're on the way. Don't degrade your eye sensitivity by looking at Jupiter or Venus. First of all, you've got to make sure the moon isn't anywhere in the sky. Because if your moon is in the sky, even if it comes up very late, don't forget the later it comes up, the more closer it's going to come up to Subha Sadiq. So you need to make sure it's totally moonless night. Now don't degrade your eye sensitivity. Don't look at Venus or Jupiter too much. I mean, I've seen the equations, and like the human eye can pick up a candle from a distance of 700 meters in perfect night conditions from a distance of 700 meters. So imagine a candle at 700 meters away, right? So if you're observing Venus, which God knows, a couple of million miles away, it's a pinprick, right? And it's so bright that you're going to degrade your night vision. So you should be careful about these objects. You basically, the best way of doing an observation is having a dark box or a total pitch black tent. The only thing that's exposed is the horizon, and you're basically just waiting for that moment to come up. Keep your task in mind and try to see contrast between horizon and the meridian. So basically, what you're trying to do is don't look at your watch. Like some people know what time Fajr is, right? The earliest time for Fajr. Don't look at that, because then even if you don't see Fajr, you're going to think, I should have seen it. Yes, I've seen it. Try to see it for yourself. Right? So like an hour before Fajr, stop looking at your watch. Just look at that point, because you're going to miss it otherwise. By a few minutes, you've missed it, and your timings are going to come out different from what they actually are. So try to see the contrast. Try to see the difference now. Can you see the horizon from the sky? Can you see the land mass? Or can you not see it still? Is it still invisible? And the minute you start to see it, you know it's Fajr's appearing. Crucial, you don't look at the time, okay? write down whatever you observe, how long it lasts, and the time. So whatever you observe, write it down, how long the phenomena lasted, and what time it was, because you're going to tally up with other people. And if you're the only one that saw this, and nobody else saw this, well then you've got to carry on your experiments until you work out that nobody else can see this because your eyesight's better, or you're seeing something that's, you know, the light is playing tricks on you, the darkness is playing tricks on you, and they are seeing something and you're not. Okay, timetable considerations. Now, when you make timetables, most of our timetables, even the correct ones, are given for, we're getting them from observatories. Right? And now, the problems with observatory timetables is they're not universal. They're made at ground level. Now, we've got to take in elevation above ground. Times are given for sea level only. City elevation needs to be looked at. So, for example, now, my city could be several hundred meters above sea level. Wales, if you go to Wales, you're going to be at least 500 meters above sea level, depending on where you are. Scotland and you know, some of these cities, even London, right? You're about 60 meters or whatever above sea. I'm sure. I don't think London is, but you know, Birmingham and these cities. So your vantage point is greater. The higher you go, the further down the horizon you can see. So even though the sun for Maghrib has set completely at ground level where you are, it's maybe not. Right? Now the formula is for every 1,000 meters you go up, it's about a degree. It's about 60 arc minutes, which is about a couple of minutes, 4 minutes. But the thing is, it's enough. You've got to factor it in, and we don't do that. Right? So we need to do this for our timetables. Topography. How do I know that just on the edge of my horizon, I think it's about 30 miles away, there's a hill or there's a mountain, right? So the sun's going down behind that, but actually it's not going down below the horizon. So altitude, latitudinal differences. So like for argument's sake, many times you're going to see a timetable and you're going to get the time for say Fajr or Isha or Maghrib, and like it's not going to match perfectly your time. That's because that sighted observation was probably somewhere halfway into the interior of the country, and maybe you're right at the bottom edge of the country. So you are now a few minutes away from those times. Or you could be left or right by an hour from GMT 0, Greenwich. The Greenwich University measures its times from 0 longitude. You could be this way. I mean, if local timetables were made, for argument's sake, for Essex, could you use them in Reading? You're probably going to get a lag of 30 seconds, right? That 30 seconds is crucial if you're trying to pray and run off to work or whatever it may be. So that's why you need to take into account your no one timetable is enough for the whole country. I think it's every 30 miles you need to work on a different timetable. So atmospheric refraction. Right now, the atmosphere it's obviously like a lens, right? So when you see something in the sky, depending on how thick that part of the lens is, it's not exactly where you see it. So when you see the sun go down below the horizon, you're not actually seeing it. It's already gone down. So when you see the bottom part hit the horizon, the top of it's already gone down. So technically, the sun has disappeared and it's Maghrib. But we go by optical sightings, so obviously we would still look for the sun to go down. But this is important to know because timetables factor this in. And depending on how hastily you download a timetable from wherever you're getting your timetables from observatories, they may give you refracted times or non-refracted times. If they're giving you non-refracted times, then you're going to get an earlier Maghrib, whereas the sun is still visible, but you've just not bothered to look at the sky. So it's very important that we understand refraction as well, and we need to know how our observatory works. So atmospheric refraction is 0 at the zenith. At the zenith, at the top, it's 0. But as you move down, right, one arc at 45 degrees latitude is still only 5 at 10 degrees, but then quickly increases because the atmosphere, you're seeing through more of the atmosphere now. So when the horizon is approached, so on the horizon itself, it's about 34 arc minutes, which is just over the size of the solar disk. The solar disk is 32 arc minutes. So it's okay. So times are calculated. The HM Nautical Almanac. Now the times are calculated proximate. I spoke to Steve Bell and I asked him about this. He says that we never observe. Now due to atmospheric refraction, they factored that in as well, and I'll tell you how they factored that in. So sunset and sunrise is when the upper limit is on the horizon. But when they chart their times from 18 degrees below the horizon, it's from the solar disk it's from the middle of the solar disk. So even when it's above your head, it's from the middle of the solar disk. So when they get down to the horizon, all of a sudden they've got to do a jump. Right? And that causes problems for their timings, because now you're not going by the middle of the solar disk, you're going by the top. And plus you've got atmospheric refraction as well. So assume a mean refraction value of 34 arc minutes and a semi-diameter for the sun at 16 arc minutes. So 16, 16, 32, which is the diameter of the sun, I'll explain to you on the next sheet. Consequently, when the upper limb of the sun is on the horizon, the center of the sun is actually 50 arc minutes from the center, below the horizon. The time taken for the sun to cross the horizon at sunrise and sunset varies throughout the year and for different latitudes. So for 52 degrees, which is just above us, it ranges between 3.45 minutes and 4.55. So almost 5 minutes in the summer it takes for the sun to go down. So here's an example. Here's the horizon. So you got, this is where they measure it from when it's up there, right? So the minute it hits this, they've got to change their calculations now because they've got to measure it from the top. So this is where the sun actually is, right? But you're seeing it here. So when you see the bottom part of the sun hit the horizon, it's already gone below the horizon totally by about two arc minutes over. So then when they do the measurements, they've got to do 34. Yeah, so it's here. So it's 50 degrees from there, and from there they've got to recalculate and give you the times from there moving downwards. So the difference between, okay, again this is the same thing I just showed you. Atmospheric refraction. The sun's about down here, so 90 degrees, it's the same thing. Okay, leap year, another interesting thing. We're going to be wrapping up soon. So the Earth goes around the sun. Do you remember in the beginning I said to you it goes around the sun in 365.25 days? Now there was a reason for saying 25 days. Now before a leap year calendar was used, Pope Gregory introduced the idea of putting a leap year into the calendar. Why? Because the festival of Easter was falling behind one of the European pagan festivals. As you know, Christianity, the Catholics, the way they converted most of the pagan Europeans was by Christianizing their festivals. That's why, with Christmas and with Easter and everything, they're pagan festivals really. The 12 days of Christmas, the burning of the fire, the fir tree, the harvest time, Lent, and everything. So it was falling behind by a few days. So they wanted to fix it and make sure that those two festivals coincided. So they added the leap year. Now, you can do this at any point. They just chose that particular date. Other calendars, Iranian calendar, you've got the Chinese calendars, the Indian calendars. Most of them are lunar calendars, but they have lunisolar calendars where they kind of combine both of them. And you may be adding a whole month at certain points after a few years. So, but for the Gregorian calendar, it's a day every 4 years. So, do you remember I said to you 365 days, 0.25? That's a quarter day. So every year you're a quarter day behind in your calendar. So 4 years you're now 1 whole day behind in your calendar, and 1 whole day is a 5-minute prayer time difference. Even more depending on where you are. And on a daily basis, it's a minute or so. Right? So year in, year out, we're using timetables that were printed 20 years ago, and we're using them year in, year out, year in, year out. We have to print timetables that are location-based, elevation-based, and yearly-based. We have to print them out yearly. So look, before a leap year calendar was used, the seasons drifted around the calendar. The drift is about quarter day or 6 hours each year. For example, over 300 years, July would end up in spring. If we didn't correct it over 300 years, your July wouldn't be summer, it would be in spring. Because our calendar doesn't match what's actually happening in the horizons. It's a bit difficult to do that. So how does that affect prayer times? Times need to be updated yearly, otherwise they too would be left behind. So here's an example. Now you've got, these are the winter times for Salah. So 2012, dawn is at 6 o'clock. Right? That's the crack of dawn, as-subh sadiq. You've got to 8:04 to pray Fajr, right? And your your Maghrib is at 15:54. So that's 3:54 is Maghrib. But in the summer, if you look at here, 5:21. The reason I chose the date 21 is because this is the last day before you can no longer calculate Fajr and Isha for 2 months. So this is the last day where you can observe Fajr and Isha times. Over here, Fajr starts at 1:26 in the morning. Isha is at 12:42. So you've only got like less than an hour, right? You've got 58 minutes between Isha and Fajr. Imagine fasting that long. So as you can see, look, this is the same date on the for 2012, 2013, 2014, and 15. Now look at the time changes. Right? Because of the lag, the 6 hours. Salah time, your Isha time, 2012 is 24:42. Then it goes to 24:37. So you've got over 10-minute gap in just one year. Then it goes to 34, and then it corrects itself. Every 4 years, you've got 4 years, so 2011, 12, 13, 14, 15, 15 it corrects itself again. So when they correct their timetable every 4 years, you're going to get back to the same dates. And then it moves on 4 years, and then they correct it again. Which means, but can you see the time difference? Look, 34, 42. Right? So if you don't factor this in, you're going to have prayer times that are going to be a bit out. Maghrib time, you're out by a minute or so. So not only have you got to factor in elevation, you've also got to factor in your leap times. So the reason I've put this in red is because, do you remember I said this is the last day where you can observe Isha and Fajr. From the next day, you can't observe Isha, and the day after, you can't observe Fajr and Isha. Right? But over the 4-year gap, we move back by a day, a whole day. So the day changes. Now it's 2 days, right? So it's the 22nd, which is the last day where you can observe Fajr and Isha. 22nd is the last day where you can observe. The rest is the 21st. Right? So you've actually moved back a whole day, or forward, or wherever it is. So Alama ibn Qadamah ibn Hamli writes, there is no difference in the scholars that the time for Isha commences when Shafaq occurs. So everyone says when twilight, the time for Isha commences, there is only a minor difference between the sayings as to exactly when Shafaq is said to have occurred. Some say Shafaq occurs when the red light after Maghrib disappears. Others say it is when the white light disappears. So these are some very famous personalities. Ibn Umar and Ibn Abbas, right? Mujahid, Sa'id ibn Jubair, these guys, Imam Thawri, all these guys, Imam Malik, Imam Ahmad, Imam Shafi'i, Imam Abu Yusuf, they said when the red light disappears. Now, Anas ibn Malik, Abu Huraira, great personalities, Umar bin Abdul Aziz, Imam Uzay, Imam Abu Hanifa, they state that it's when the whiteness disappears. Is their reference there? So now you've got great personalities saying redness and great personalities saying whiteness. So why is it that in England we still insist that we pray at 18 degrees solar depression? The reason for that is it's between 12.5 and 15 degrees that the redness disappears. Now in England, because it takes 4 hours for twilight to commence into complete darkness, you're not going to be in a clear position to determine where the redness actually disappears. It's such a fine line, it's very difficult. Different mushahidas will give you different timings for the redness to disappear. So you're in doubt as to when to implement that rule of redness disappearing. That's when Taqi Usmani says 99.9% of India Pak ulama say the time for Isha in England commences at 18. To be safe, pray your Isha at 18 degrees below and not before. So here we go, look, 99%. So Imam Abu Yusuf, again, this ease of the ummah. That's the reason why we do actually have leeway. I'll tell you why we do have leeway. Now these are the time differences. 18 degrees, 17.5, 15 and 12 degrees. Now some timetables in England are still running on 12 degrees. The majority are running on 15 degrees. And we're trying to get a drive in now where we're trying to get people to run in on 18 degrees. Now look at the time difference. This is 18 degrees. Your Isha is at 24. Actually, Fajr is more important to look at. 126 is Fajr, right? According to 12 degrees, 3:17. So you've eaten 2 hours into your fast time if you follow a 12-degree timetable. Even if you follow a 17.5-degree timetable, look at the time difference. So just a half a degree, right? it's 20 minutes. 2 hours over here. So these guys who follow 12 degrees are eating into there. And I remember our mosque timetable when I was young. I remember the time for July and May. It was around that time. There were 12 degrees for the last 20 years. Right? I've not seen the timetable in my mosque change. Right? Even now they changed it, but they didn't do a proper job of it. It's not 18 degrees. So like this Ramadan, I knew which mosques had 18 degrees and which timetables to follow. And I knew which mosques weren't doing it. Right? And like even certain friends of mine, they were following certain timetables. Like, brother, you can close your fast, it's fine, and you can do this. And I'm like, no, I'm going to close my fast before you because I've seen it. Right? I know what the astronomical data says, and I'm not going to follow this mosque. And if you ask the mosque where you get your timetables from, this mosque says, oh, we got it from this mosque, from this mosque, from this mosque, from this mosque, and so it carries on. And these timetables are like 20, 30 years old. So dispensations, so you've just seen the times for Fajr and Isha now, right? They're at such extremes that how can you possibly pray your Isha and then pray your Fajr, in like a 1 hour gap? And if you got a 3 hour gap between Tarawih, how are you going to read Tarawih? And you've got a 3 hour gap between your fast and your with the fast you can't really play about much, but with your prayer there's dispensations. So what is the solution for perpetual twilight? Now, in this condition, it is necessary to still pray Fajr and Isha due to the hadith of the Dajjal. So basically, your Fajr, even if Fajr doesn't kick in, even if Isha doesn't kick in, which means you're not going to get a Fajr, we still have to pray. So we still have like a biological cycle. We still have a cycle. You're still getting the day and night, right? Even though you're not seeing it. So what's the solution? There's a hadith in Sahih Muslim. It's to do with the end of times. It's when the Dajjal will come. It's one of the signs. There will become a time when there will be a day like a year, a day like a month, and a day like a week. The people asked him, sallallahu alaihi wasallam, if during the day like a year, should they offer each prayer only once? He replied, you should approximate the times. Right? So that's what's happening. This is happening on a daily basis for those 2 months in England, 3 months in Scotland. Right? So you've got to approximate your times. So you should approximate the times. Now there's 4 dispensations given by the ulama. There's Aqrabul Ayyam, Aqrabul Balad, and Nisful Layl, and 1/7 of the night. Now any 4 of these options are valid for our areas during those months. And even outside of those months, when your Isha time gets very late, you can implement these. But it's important to implement them as a collective community. So the nearest day to use Fajr and Isha times from the last day before persistent twilight. So basically for London that would be on the 21st of July to 19th of August. Now this is the last day you can measure Fajr and Isha. Right? So what you do is you set this day for the next 2 months. So every day your fast, your sahuri will be the same time, your Fajr will be the same time, your Isha will be the same time, your Maghrib will be the same time. There will be no change. Your nearest latitude. So that would be to follow the timings of a city or place where the signs of Suba Sadiq are easily distinguishable. So for us, that's somewhere in France. I think it's Bordeaux. The city of Bordeaux is the nearest city to us where you do get the twilight does disappear. Again, Suhoor will follow the time of that city, not your city no more. So middle of the night. So we know when the sun rises. We know when the sun goes down. We may not be clear on what happens in between, but we know what happens here and what happens here. So what you do is you half the night. Now you make 1/2 for Isha, 1/2 for Fajr. So you pray your Maghrib, and after a time that the ulama stipulate, that's Isha now. Straight after that, any time after that, you can pray your Fajr. Suhoor would end at your midpoint. So when Fajr kicks in, even though the alamat, the signs are not visible to you, Fajr has kicked in and you stop eating. Then you've got 1/7 of the night. You divide the time between sunset and sunrise into 7 parts. Right? So the first 7th from Maghrib, from sundown, the first 7th is Maghrib. The second 7th, all the way to the last 7th, is Isha time. And then the last 7th is your Fajr time. Right? It's a bit complicated, but that's how they do it. So your Suhoor ends on your last 7th. Yeah, this is an option as well. Now each method has its benefits depending on your community. It's what your community come together as a whole and decide. Now some mosques in England, when Wifaq ul-Ulama and these people approached these mosques and said this is the evidence, You need to follow these times. Why are you not following these times? They said, we want ease for the ulama. We want ease for the ummah. Right? So we will give them an easy time. But you're contravening scientific evidence. You're contravening the Sharia. Right? But just to make it ease for the people, and where are they getting these understandings from? So any of these methods can be followed. I mean, this is ease. Because when you follow these methods can be followed after the spring equinox. Because after the spring equinox, our days start to get longer than its nights. And very soon you'll find Isha is at 10. And it gets very late. So the ulama use these dispensations and then you factor them in. So even if you're 2-3 months away from perpetual twilight, you can start factoring these. So this is Shari ease. This is ease that the Deen has given us. This is not ease that you're making from yourself. You're pulling out your pocket and saying, okay, we're going to set these timetables because we want your money. We want you to keep coming in and not going to the other mosque because we want you to pay into our coffers. It is important for the community or city to come together and decide upon a method that will make it easy for the people. So Imam Nawawi mentions these methods in his work. So this is nothing new, right? It's been discussed with the ulama of the old, Rawdatul Talibin in his commentary of Sahih Muslim. Ibn Abidin Shami in his Radul Mukhtar, he discusses these. And you can get the fatwa of Muhammad ibn Adan al-Qawthari and Mufti Taqi Usmani. They have given fatwa on this as well. If you need updated timetables, you can contact me, not because I'm a great person or anything, only because I'm familiar with the science of astronomy and I've got access to resources and timetables. If not, you can go to the website of Wifaq al-Ulama. This is their address. They do yearly updated timetables for location as well. So if you're living in Birmingham, they'll give you Birmingham timetable. If you're living in Nottingham, it's close. But again, you're going to get minute variations. HM Nautical Almanac has a degree-based timetable, but they don't take elevation, sunset, solar disk. Okay, you don't need to worry about that. They have made an Islamic timetable complete with Hanafi and other Imam Asr times. So if you go to this website, you can actually print off the Islamic timetable there. So what you need to do is, remember I told you about elevation? Add 4 or 5 minutes to the start of Maghrib and take away 2 or 3 minutes for Fajr. Yeah, because it's at ground level. And nobody's at sea level. I mean, here in Jizan, we are technically at sea level. So if we get a printed timetable, you can follow it blindly. But anywhere else, you're going to be on an elevated ground. So you need to add, it's important that when you do look at any timetable, considering most timetables are not accurate anyway, that you have to add in times. Even if it's 18 degrees, you have to add in 2 degrees, 2 minutes to 4 minutes for Fajr, for Maghrib, and take away that time. Because you're elevated, you're seeing the sunrise quicker, right? They also do moon visibility charts as well. So if you want to find out, is it Eid or not? Yeah, and why is Saudi and the rest of the world doing Eid when the moon's not visible? They'll tell you that as well. So just some personal observations from myself. Now, Muslims have been at the vanguard of this science for 1,000 years. We really developed this science. We were at the forefront, the cutting edge of this science. Everything of what is built on traditional astronomy now comes from the East, comes from Islam specifically. Solar and moon sighting problems have only become about due to lack of basic astronomical knowledge. Now, it's very important to know your moon times. A woman's iddah, her 3-month period, is down to moon sighting. A maintenance that a widow receives, again, the waiting period is from your moon sighting. Your Eid, your Hajj, your Ramadan, your calculating of your 27 nights, the odd nights are all done by the moon. So it's very important that you know the moon. Second thing is that, this is for another talk, it's very important to know when to pray and fast, right? So astronomy should be introduced back into the curriculum. It used to be a core element alongside of Tib, Islamic medicine. Why? Because the Islamic the ulama, the muftis, the faqihs, they had such a huge role of responsibility on their shoulders that they were taught the science of tib so they could heal themselves, right? And in times of need, they could earn a bread. People could come to them. People would come to them and they'd earn a living by that as well. Today, it's not taught in the curriculum. Traditional tib is not taught in the curriculum. And astronomy, I mean, people will spend 8, 10, 15 years in our madaris and they'll come out knowing zero scientific knowledge, zero secular ilm. Now these ulama in today's 21st century, where we've got huge amount of Muslims living in the West, facing these problems, even in the East, we're so far behind now. Now these sciences, we need to revive our madaris. We need to get these sciences and other secular sciences into our madaris so we can produce complete humans, right? Who not only know deen, complete scholars, they know dunya as well. And that's lacking. I mean, in most of our mosques in England, you're probably aware of this. You're probably aware that when we need an imam, they'll phone their village back home, or they'll phone a madrasa in Pakistan or India or wherever they're from and call him over. Now this guy, who's only religiously educated, he's totally uneducated when it comes to the secular sciences. He spent his some part of his youth isolated in the madrasa. He doesn't know what social problems we face, issues with teen pregnancies, drugs, sex, disrespect to peer pressure. He doesn't know anything about this. And he speaks a foreign language. Most of the youth cannot speak his language. How are they going to see him as a leader of the community or role model who's going to guide them? So our leaders are actually alienating our youth even more from what's really happening. By insisting that no, we're not going to produce homegrown scholars, and the ones that are produced, we're not even going to invite them into the mosque because of what their aqidah may not be sound, this may not be sound, he may have a problem with this. But what we're going to do is we're going to call somebody who's got totally no understanding of the first world, and we're going to call him here, and hopefully he's going to sort your problems out that you have with, subhanAllah, this is our thinking at the moment. And this is why the Muslim world's in a mess. In 1969, America sent a man to the moon. And if you look at the physics and the mathematics that went into the rocket science, and then that went into the calculations of where the moon is, subhanAllah, right? And we're 1400 years, 1,000 years after our astronomers were at the forefront of this, we still don't know where the moon is, right? They sent a man to the moon and we still don't know where the moon is, and we still don't know the time of Fajr, right? So this just gives you, just tells you how bad it really is. Okay. Wa akhiru da'wana alhamdulillahi rabbil alameen. Thank you very much. Any questions? Okay, thanks. Allah reward you for this, man. Do you know what it is, Andrew? My heart and soul wasn't into this. I didn't smile, nothing. I'm tired. 1 hour, 47 minutes.